section that we're going to cover is going to be 3.5. This 3.5 is going to be, it's a kind of new limits. It's a limits at infinity. So you want to know what would happen to the value of the function when the value of x is going to be extreme. Extreme means extreme to the right, extreme to the left. So this means increasing without bounds, x goes to positive infinity, or decreasing without bound, x goes to negative infinity. This is what we're going to look into it. This section is usually in some other textbook discussed at the early pages, if you like. But we discuss it here in your book because they want to use it in order to sketch the graph of a function. And otherwise, in fact, this is the only limit that you are going to use for calculus 2. Okay, so it's not bad. Sometimes I cover it at the beginning. It's not too bad to cover it now. So you are going to remember it for calculus 2. It's going to be very easy concept, and I'm going to give a shortcut that's going to be very useful for you if you take calculus 2 or otherwise in general. Okay, so 3.5 is it's different from whatever we did. We pause if you like, and that's why sometimes we discuss this concept right at the beginning, because this is not going to be anything to the derivative at the moment. Okay, so this is it. We want to know how we're going to find the limits. Okay, limits at infinity. We're going to combine them in with another limits that we're going to discuss right at the end of the course. Okay, limit at infinities. Limit at infinity, and if you have done this one a little bit without any notion of the limits in your pre-calculus course or college algebra, so I prefer to call it end behavior of a function. That gives us a better understanding of the concept. So just to remind you what you did in algebra, so this is also, we may think about it as end behavior. Okay, and behavior of functions. It's going to be the same thing. Okay, this is the way you discuss it in algebra. And of course, we would like to use the tool of calculus to talk about it. So as I talk about it, if x increases or decreases without bound, then we investigated what would happen to the value of the function. For discussing that idea, we are going to use the limit at infinity. So this is it, the behavior. Okay, the behavior of a function of the value of the values. Okay, of a function, that the values are going to be f of x. Okay, as x increases or decreases, getting bigger and bigger and getting smaller and smaller. Okay, increases or decreases without bound, it means goes to infinity. Without the bound, that would be easier to remember, to understand. It's going to be called, okay, this is going to be called its end behavior, the end behavior, the end, okay, the end behavior of the function. So that's to remind you what you did in algebra. Now, tool of calculus, we are going to use the notation of the limits to think about it or to talk about it. Now, when x increases without bound, when x increases without bound, if increases without bound, we are going to use this notation. We write x goes to positive infinity. So this means x is bigger than any number that you think about it. So if you fix a number like 10,000, so there is a value of x which is bigger than 10,000. This is what does it mean? Okay, and when x decreases, getting smaller and smaller, decreases, again without, okay, without bond, going to the negative infinity this time. We are going to write, okay, we write x goes to negative infinity. Okay, x goes to negative infinity means, you know, if you think about any number, any small number, if you like, then x is going to be less than that number. Okay, that's going to be one. There is a notion if we're going to be math major, you have to write this positive infinity and negative infinity. But if you write just infinity and you're going to be math major, there is going to be another interpretation of this one. If you write x goes to infinity, then you have to think about absolute value of x getting bigger and bigger and bigger, you know. But in this course and in your textbook, anytime they write infinity, they mean positive infinity. But I always write it down just to, you know, to emphasize that there is a difference. Okay, but not a big deal in this course. So we are going to use the notion of the limits to investigate it. Okay, we use the notion of the limits, limit of f of x, because we know it. X goes to, okay, positive infinity for the first one, and x limit of f of x, x goes to negative infinity for the other one. Okay, this is it to study in behavior or those limits. Okay, and behaviors of the function. Okay, of the function function. Okay, as soon as you write the limits, we know what we are talking about. The only difficulty is when x goes to positive infinity. The positive infinity is not a number. It's a concept, description, and we already describe it. So, for example, if you want to identify it, again, you can write it down in more details, but it's some more abstract course. So therefore, when we write a limit of f of x, for example, x goes to positive infinity to be equal to the L, is like the one that we did before. So this means the values of f of x can be estimated by L when x increases without bond. Okay, so the same thing of everything you talk about it before for the limits can be applied. So if and only if f of x can be estimated, it's going to be almost L whenever x increases without bond. X increases. Okay, x increases without bond. Okay, so that's going to be the one. Again, you know, you can say that I can estimate f of x by L as you like, if you like, as we did it before, by picking the proper number for the x here. So it's going to be the case, and similarly, of course, limit at infinity can be defined similarly. Okay, so similarly, when the limit of f of x goes to negative infinity, we write it down as L. So this means I can estimate the value of f of x by L. This time, whenever x decreases without bond, getting smaller and smaller, decreases without bond. So very brief format that we're going to use in calculus 1. So since it's a notion of the limit, so all the theorems that we did before can be applied. Okay, squeeze theorem, okay, then the idea of sum of the limits of the sums, okay, the product rule, you know, the quotient of the limits, everything can be applied. But we are going to make it short. So how are we going to make it short? We use a little bit of geometry. So we are going to look into some special function, and then as usual, we are going to create a theorem for the polynomials, and then we use the polynomials to take care of the others, okay? So these are going to be the preliminaries. So let's say I get a couple of examples to be able to generalize it for we take care of the power function first. Okay, so for example, if you want to find each limit, that would take us to the polynomials, and this is what we need. Okay, so for example, if you want to find what is going to be the limit of x squared, okay, x squared when x goes to negative infinity, this is going to be the one, and then you want to know what is going to be the limit of x squared when x goes to positive infinity. Okay, that's going to be the one. So, to get the idea, you can check the graph of this function. You see, if you check the graph of the function, so if you consider the graph, this is how we do it in algebra. Consider the graph of y equal to the x squared. You see, this is going to be a parabola. Okay, so your graph is going to be a parabola. So this is it. We get the parabola here. So this is going to be y equal to the x squared. You see, y equal to the x squared. So this is going to be from negative infinity to positive infinity for the domain. And the y value going from negative infinity to positive infinity over here. You see, just check. So as you can see, the function, the function is above the x-axis all the time. So if you want to think about the values of the y are all positive, up, 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 up. So when x goes to negative infinity, you're coming from here. You see, if you pick a number here, so this is going to be the value of the function. If you pick a number here, this is going to be the value of the function. So as you can see, when you go from left to right, the value of the function is always up, up, up. So this means the limit of, okay, so this means the limit of x squared. When x goes to negative infinity, eventually it's going to be a positive infinity. Okay, that's going to be mine. Okay, up, 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 forever. And it's going to be the same for the other way around. Okay, the other way around, if you pick a number, if you're coming from here, if you're going away, if you like, if you're going away, this is it, getting bigger and bigger and bigger. So again, the value of your function is up, 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 up. So this means the limit of the x squared when x goes to positive infinity would be just a positive infinity again. Okay, so that's going to be the argument that you are going to have over here. Okay, because the power is even. You see, the power is even, so the result must be positive. So x getting in both cases without a sign getting bigger and bigger and bigger. So in that case, the result would be a positive infinity. Any question? So this would can happen for, okay, we can check it. So that's going to be the case for number one. Any question? So this is for the even power. So it doesn't matter if it's going to be x to the 4th, x to the 6th, x to the 8th, you get the same answer. So because the power is even, so the result would be a positive infinity again. So that would take care of the even power. Any question? Let's check one odd power and then make an observation as a theorem and then be done with the powers. Okay, how about x cubed? So the second example is going to be, we want to investigate. We do one odd and one even, then we generalize it, okay? So this is going to be the second example. You want to know what's going to be the limit of x cubed. Okay, limit of x cubed when x goes to negative infinity. And we want to find what is the limit of x cubed when x goes to positive infinity. Again, if you look at the y equal to the x cubed, this is going to be y equal to the x cubed. If you graph it, you see this is going to be the graph of the y equal to the x cubed. Okay, y equal to the x cubed. So as you can see, the x going from left to right, from negative infinity to positive infinity, the domain of the function. And the range of the function is up, up, up. You get a positive infinity here, and you get a negative infinity here. Again, you see you don't have any difficulty for this one. If you look at it, x getting bigger and bigger, so x cubed would follow the same thing. So if you pick any number here, you see, let's start with negative infinity. When x goes to negative infinity, you're coming from this side to the graph. So if you pick a number here, the value of your function is here. If you pick a number here, the value of your function is going to be here. So as you move from negative infinity, x goes to negative infinity. So the function going down, 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 which is a negative infinity. Okay, so that will tell you that the limit of x cubed, when x goes to negative infinity, it would be negative infinity. Okay, algebraically, it's clear because the negative to the third power would be negative, and the quantity is infinity again. Okay, but if x goes to positive infinity, you are here. You see, if you get a value for the positive infinity, value for x, positive infinity. So again, these are going to be getting up, up, up here. So this means that the limit of, okay, the limit of x cubed when x goes to positive infinity is going to be equal to the positive infinity. And basically, you know that it's a positive to the third power would be positive, negative to the third power would be negative. But since it's the power of the number, the result is the infinity as we did it. Any question? So let's make a generalization that we're going to use it, and that's going to be the conclusion for the power function. So what is going to be this observation? We need this one. That will be so helpful. So let's say if you can make a general formula for all these type of functions. So suppose you want to find the limit of, you see the limit of x to the n. N is any positive integer. Okay, this is going to be the case. And then you want to find this limit, let's say when x goes to, okay, when x goes to positive infinity, we have nothing to worry about here. You see, when x goes to positive infinity, since it's a positive, you raise it to any power, would be positive again. So this result is going to be a positive infinity. Okay, for any, okay, n integer. Okay, integer n, which is going to be, greater than equal, greater than 0 if you like. That's going to be the one. Okay, x squared to the 5th to the 6th, etc. All of them would be give you a positive infinity, or for any number, any positive number. Okay, so for any positive number, you are going to have, you're going to have this case. Okay, but how about if x goes to negative? Okay, if limit of x goes to n, x goes to negative infinity. Okay, any suggestion for this one? You see, when x goes to negative infinity, we cannot do it right over here. So it depends on this power. If the power is going to be even number, negative to the even power would be positive. So you have to break it in two parts. You see, look at this one. You have to break it in two parts. It's going to be a positive infinity. It's going to be positive infinity, but if n is even number, n is equal to the, let's say 2, 4, 6, etc. So limit of x squared, x to the 4th, x to the 6th, x to the 8th are all positive infinity. Okay, but if n happen to be an odd number, you see if x is equal to the 1, x equal to the 3, 5, then negative to the odd power would be negative. So in that case, you get the negative infinity when n is equal to the 1, 3, 5, etc. Okay, so basically, if you get the power function, you're just focusing on the power. The result is infinity, and you have to determine the sign. It depends whether, okay, in this case, if it's going to be positive infinity, nothing to worry about because the result's positive. but it's going to be negative infinity. As you can see, it depends on the power of the n to be able to take care of it. So that will take care of the monomials function, if you like, okay? Or the power function, power of the x. Any question? So let's get some examples to see how we're going to operate. So example, we wanted to find each limit. Okay, find each limit. Let's see if we can do it. The first one. The first one, we would like to find the limit of, okay, limit of, let's say 5x to the 4. 5x to the 4, but x goes to negative infinity. Let's see. You see 5 is a number, it's a positive number. So you keep the 5, then you take the limit of the x to the 4. You know, I explained it, but you can write it down in the short form. You see, as we did with all the other limits, so the limit of the 5, x to the 4th, when x goes to negative infinity, is going to be 5 times the limit of x to the 4th, okay, when x goes to negative infinity. Now, when x goes to negative infinity, this is even power. So the result would be a positive infinity. You see this one? This one would be a positive infinity. But 5 times a positive infinity, you know, 5, this is increasing without bound. The 5 is positive, so positive would be positive. So this result would be just a positive infinity. Okay, so the limit of the 5x to the 4th when x goes to negative infinity would be positive infinity. Any question? Let's see if we can do this one. How about this one? How about the limit of, okay, the limit of, let's say, in negative 4, okay, negative 4 x to the 3rd, but x goes to negative infinity. Any suggestion for this one? Is it positive infinity or is it a negative infinity? The solution. Anyone want to try? Limit of x goes to negative infinity. I just put this one inside the parentheses, you know it. Let's see, we have one answer. Geneva, positive infinity, Brian on negative infinity. No, positive infinity is correct. Positive infinity, look at this one. We focus on this power first. You see x goes to negative infinity. Negative to the odd power would be negative. But there is a negative 4 here. So negative would be positive, okay? So you go with the power first, then they may, you may have a number. So you have to take care of that one too, okay? So this is going to be the solution. We do it right away, I just explain it. So this is it, this is what would happen for x cubed when x goes to negative infinity. You can negative, it's like a negative 4 limit of x cubed, x goes to negative infinity. You see, negative to the odd power would be negative. So this part over here, you see this part over here is going to be a negative infinity, but you have a negative 4 here. So negative times negative would be positive. So the result would be a positive infinity. Okay, so be aware of those coefficients that we are going to have. Any question? So that's a power function. So why we did the power function? Because our first group of functions are going to be polynomials. Remember, the polynomial, just a combination of powers of x. You just put a couple of these powers together, and that would, okay, you just put them together, and then that give you the result. So for the case of the polynomials, we have a nice theorem. You did have this theorem in college algebra, and that will tell you that, you see, the end behavior means the extremes values of the function. The value of the function when x getting to these extremes, positive infinity or negative infinity. If you have a polynomial, you have a combination of these. And you know that these are going to be either positive infinity or negative infinity. So that theorem will give you this idea that the end behavior of a polynomial function is similar or equal to the end behavior of its leading term. You know that the leading term in a polynomial is the term that contains highest power of the x. So this means if you have a polynomial, we say we shrink it. We shrink it into the one with the highest power. Then we check one of these. That's great theorem. And that would be so useful for you. It's not in your book in this interpretation that I'm talking about. That this would be so useful for you because that gives us a shortcut for the rest of these sections, which is very much different from your book. It would be very easy for calculus too. And this is in fact what will happen at the beginning, okay? And if you are going to be a computer science major, you are going to use this type of ideas without notion of the limits. I'm going to show you in a minute, okay? So that would take care of the power functions, this positive, negative, infinity. Now the big one is, how about the end behavior of a polynomial? So how are we going to find the limit of a polynomial at infinity, okay? Pay attention to this theorem, which is going to be so useful for us, okay? And historically, this is the way it's been done. Although, you know, in calculus, we have other methods to discuss this. Okay, so this is it. That will take care of the polynomial problems. So what's going to be end behavior or just the limit at infinity? Okay, and the behavior of a polynomial. Okay, polynomial function. So for the polynomial function, that's it, the end behavior of a polynomial. So this means the end behavior. Okay, end behavior of a polynomial function, is going to be similar, the same, similar to the, okay, similar to the end behavior and behavior, okay, and behavior of its leading term, leading term, because you know that a polynomial is a combination of terms or monomials. Leading term, what is leading term? It's going to be its highest degree. It's going to be its higher degree term. So when we say, you know, the degree is 2, degree is 3, you're just looking at the leading term. And we write the polynomial, you know that we start with the highest power and just we keep going down. So this means if you want to check the end behavior or the limit at the infinity of a polynomial, we say shrink it. This means you just look at its leading term. So I'll give an example to see what we are talking about. That is your first serious problem or first serious case for the limit at infinity. Okay, are you ready? Find each limit. Find each limit. So the first case is this one. First case, the limit of 5x cubed. Okay, 5x cubed minus 4x squared plus 3x minus 10. This is it. You want to find this one when x goes to negative infinity. You see, this is the polynomial. What is the leading term? This is the leading term, the term containing the highest power. So this will tell you that the limit of this polynomial at infinity is the same as the limit of its leading term. Leading term is 5x to the third. X goes to negative infinity. We already talked about it. Negative to the third power would be negative. And a 5 is a positive number, so the result would be negative infinity. This is the way you are going to write it down. You see the solution. We say shrink it first. And this is the way you write it down. The way you are going to write it down on the test or your assignment. You see, this is going to be the case. When x goes to negative infinity, you rewrite it as it's going to be limit of its leading term. We estimate it. When x goes to negative infinity. That's it. You see x cube, when x goes to negative infinity, this would be negative because of the power. 5 is a positive number. Positive, negative would be negative. So that gives you negative infinity. And you're done. See, very easy. Very easy operation that we're going to have. Any question? This type of idea has been done, at the early days in computer science or in computing terms. They don't usually use the limit procedure. If you are going to be measuring computer science, you can get it on the internet for yourself. We have a notation, we call it big O notation. Big O notation. This is the concept that you are going to have it over there. And there's going to be similar to what we did over here, but they don't usually use the notion of the limits. So the way we are going to use that one, they say that this is it. Say that the 5x cubed minus 4x squared plus 3x minus 10 is the big O of x cubed. You see? So this means that exactly what we did over here. This means when x getting bigger and bigger, you can estimate it. Okay, the limits at infinity and the x cubed, the end behavior are going to be the same as each other. And when you do programming in computer science, you see the operations would cost you time and cost you money. So when you want to guess what is going to be the situation for a special program, so you are going to use the big O notation to estimate it. So in your case, in your programming, you do have a list of good functions like x cubed, x, power of the x, the one that they like in natural log, ln x, n ln x, they have a list. So what they do when you have the program, they say, oh, this would cost like x cubed. So we know how much, cost for you to run the program for the x cube, for example, the operation, algorithm, whatever you have. So you can guess it right away. So it's a very good one. Check on the internet for yourself. You see something like the limits or limit of the sum, limit of the product. You have the big O, for the product, for the sum. So if you are going to be measuring computer science, and not bad for yourself, just check it. When it's a face-to-face, I've given this one as an honor program for a number of the students when they took my course. Okay, but in this case, just remind you. Okay, so to just show you that this procedure has been around for a long time. Of course, in calculus, we have another notation, we call it a small o, which is going to be something similar, but these are very classic part of mathematics. So you can check it for yourself. Okay, any question? Give you another one for the polynomials. So we are done with the first group of the function. That's it. So let's check another one. You want to check this one, the limit of 4x to the 6, okay, plus 2x to the 5th, minus 10x squared, okay, plus 12. You want to find the limit at infinity, at a negative infinity of this function. Again, it's a polynomial, shrink it. So the limit of this, like, it's going to be like the limit of 4x to the 6. X to the 6 when x goes to negative infinity is positive. So the result would be positive infinity. We have to explain it. So we say we shrink it. 4x to the 6, 2x to the 5th, minus 10x squared plus 12, when x goes to negative infinity. Remember, it's equal to the limit, not just the function. Limit of 4x to the 6. Okay, x goes to negative infinity. Again, x goes to negative infinity, x to the 6, negative to the 6 would be positive, so that gives positive infinity. And the 4 is a positive number. 4 positive would be positive. So that would be a positive infinity. Okay, we shouldn't get any question. You see, when it's a polynomial, because all of them would be infinity. So we just take care of the first one. It's like, when you, if you get the jackpot on the lottery ticket, you already got something like, $600 million. So you don't care about another 10,000. So that's the situation that you have to, in this case, just for fun. So that would take care of the polynomials. We're done with the polynomial case. Okay, any question? So that would be so useful for you, okay, when you want to, those table charts, remember that we use for the first derivative test especially. So if you know these ideas, that would be helpful. And of course, when you want to graph off the function, that would be very good for us to know what's going to be the direction of the graph. Okay, so we are done with the polynomials. Next, a rational function. In order to do the rational function, we need to consider one theorem again. So this is going to be our next example. Okay, our next example is going to be how we're going to check the rational function, okay, and behavior. I just stay with this expression of rational function, rational functions. So for the rational functions, we have to, again, like the one that we did. So let's have a couple of examples that make it general, then we'll be able to do it. So let's try. What's going to be the main one that we need? Find each limit. That would be the key to the formula that we're going to give you. Okay, look at this one. Number one, you want to find the limit of 1 over x to the 4th. And when x goes to positive infinity. It's what's going to be this one. Okay, look at this one. This is a fraction. On the top, we get 1, a whole, if you like, or a pizza. Down the bottom, x goes to positive infinity. X goes to positive infinity, you know that x getting bigger and bigger and bigger. When x getting bigger and bigger, you know that x to the 4th would be again a positive infinity. So what you have a fraction. The top is 1, if you like. But the denominator getting bigger. When the denominator getting bigger and bigger, the fraction getting smaller and smaller and smaller. So when x goes to positive infinity, so it means the denominator would be the biggest that we think about it, increases without 1. In that case, the fraction would be just 0. Okay, so when x goes to positive infinity, the top is a fixed number. Think about the top as a pizza. So if you have a family pizza, for example, family pizza, and if you divide it by what? Divided by 20, 50, 60. If you divide by 10,000, if you want to, divide the pizza into 10,000 parts, what is going to be each part? What's going to be your share? It would be almost nothing. Okay, so that's why this limit is always equal to the 0. And you have to remember this because we're going to use it quite a lot. Okay, when x goes to infinity, the top is a fixed number. Think about it as a pizza. Okay, 5, 6, 7. So you have a whole, you want to divide it into infinity many parts. So the result would be nothing. So make sure you remember this one, and we're going to make it official. So the limit of, we call it pizza problem, just to remember it. Okay, when x goes to positive infinity, so this limit would be 0. Okay. So it would be similar if x goes to negative infinity. So in general, you are going to use this one in general. If you want to find the limit of, it must be a number on the top and a positive power of the x on the denominator. We call it x to the r. R must be a positive number. X goes to either positive infinity or negative infinity. This is always zero. Zero when R is positive. Okay, and all we call it a pizza problem. Okay, you have the top on the top is 1. It doesn't matter. As long as the R is positive, this infinity stayed on the denominator. Some people like to memorize that, a number divided by infinity would be 0. If you feel comfortable, we don't mind. But infinity is not a number, it's a concept, okay? Just think about it that the denominator is getting bigger and bigger. So the fraction getting smaller and smaller. So when it goes to infinity, the fraction would be 0. And then we're done. Okay, so it doesn't matter, what power you have. You see, for example, if you consider the limit of the 1 over x, okay, x to the 5th, x goes to negative infinity, this would be 0. Okay, if you have the limit of 1 over x to the 1/3, okay, x goes to positive infinity, and this would be 0. So any power, you have a fixed number on the top, which is your pizza, okay? And then you want to divide it into infinity. So in that case, you have infinity many parts, and your share is going to be, okay, it's nothing if you like. Any question? Now I'm going to use this one and the idea of the polynomials, take care of the rest. I don't need any other theorems. In your book, they give you a couple of theorems, and they stay with this method, especially if you want to take calculus 2, and then you'll be so happy to do these type of problems on the 40% of the calculus 2, okay? Are you ready? Any question on this one? Make sure you remember it. It's just a hole on the top, you divide it. Now, we can do all sort of rational functions for you. There are 3 cases. Okay, and pay attention, and we give one of these 3 cases in the future. Okay, so that was number 1. This is going to be officially the first case for the rational function. We want to find what is the limit of 3x plus 5 over 2x minus 1 when x goes to negative infinity. Now, this is the way I'm going to do it. We're just using the fact that you see this is going to be a limit of a rational function. You see, limit of the rational function is going to be limit of the top divided by the limit of the bottom. The top is a polynomial. The limit of the polynomial is the limit of its leading term, 3x. Limit of the bottom one is a polynomial. The limit would be its leading term, 2x. So this is how we are going to do it. Say that the limit of 3x plus 5 over 2x minus 1 when x goes to negative infinity is the same as the limit of its leading term. Leading term on the top, 3x. Down the bottom is 2x. We shrink it. But x and x would cancel out. So that simply give you 3/2. And you're done. See, very nice method. So you are going to be focusing on the leading term. Leading term. 3/2. Any question? I'll show you the method of your book, but I prefer this one. I'm going to use this one. Method of your book. Method 2, if you like. In your book, they divide, they like to use that pizza problem that we talk about it. So what I do is, this is it. It's going to be a limit of the 3x plus 5 over 2x minus 1. X goes to negative infinity. They look at the largest power of the x, which is 1. So they divide everything, the top and the bottom, by x. So it's going to be limit of they divide everything by x. You see x, x, and that's going to be x, and that's going to be x. Okay, highest power of the x. Now they simplify it. So you simplify these two. So that gives you the limit of, you see the top we get 3 plus 5 over x. The bottom one we get a 2 minus 1 over x. X goes to negative infinity. Okay, any question? Then they take the limit. This is the limit of the fraction. It's going to be limit of the top and the bottom. So the limit of the top is limit of the first one, which is 3 plus the second one. So this is the continue limit of x goes to negative infinity. So this is going to be 3 plus the limit of 5 over x. X goes to negative infinity. And the bottom one is a 2 minus the limit of 1 over x. X goes to negative infinity. These are going to be all pizza problem, okay? Because the pizza on the top, the infinity on the bottom, so that would be 0. That would be 0, so the limit would be 3/2. It's basically the same thing that that we did. So I do the first one, okay? This is the way we're going to operate. It's the same thing. So it would be so useful. I told you, in calculus 2, we have a concept of the sequences and series, and you use it over there quite a lot. So this is simply 3/2, and we're done. There is another method, we call it the L'Hopital rule. That is the one that we're going to discuss at the end of the course. So if you use it on the test, you won't get any points. Remember, this method for the time being only. When we get to the final exam, we can use that. But those methods are going to be used when we get more complicated function. So easy case is going to be this one. Leading term, limits. Some people, they drop the limit here. It's not. The limits are the same. So leading term on the top, down the bottom, simplify you that. Easy case. Any question? Now there are 2 more possibilities. Look at this one. And the power were the same. So you may get a case that the higher power would be on the top, higher degrees, or the higher is going to be down the bottom. So with this shrinking, everything would be nicely done. So let's have something with a higher power than the bottom. So it's going to be the limit of, okay, 2x plus 1. And this is going to be x cubed plus 5. And we want to do it when x goes to positive infinity. Okay, again, polynomials on the top and the bottom, shrink it. So the leading term, you see this is going to be your leading term. So you have to rewrite it. The limit of the 2x plus 1. Sorry. And that would be x cubed plus 5. When x goes to positive infinity, is the same as the leading term, 2x, x cubed. X goes to positive infinity. Simplify 1x. So that gives you the limit of 2 on the top, x squared on the bottom. Again, it's a pizza problem. You have the 2 pizza on the top. You want to divide by infinity. Divide it into infinity many parts. So your shade is going to be nothing. Okay, so the limit is going to be, that would be easy case. And if you do it right the way, we accept it all the time. You see? So as soon as you see the power is going to be, the power of the bottom is going to be higher than the top. So this is going to be a leftover than the denominator. So infinity will be than the denominator. So this limit is always 0. So in future, if you use it, we accept that without any proof. Okay. When the powers are the same, you see powers are the same. So the limit would be the same as the coefficient. You see 3/2. When the power of the bottom is higher, the limit would be 0 right away. Be accepted. There is a theorem in your book. But if you do the shrinking one, really, you can do all of them. Any question? Next, if the power of the top is higher. Okay, so number 4. What would happen if the power of the top is higher? So the example is this one. So the limit of x to the 5th, okay, plus 2x plus 1. And this is going to be x squared plus 7. When x goes to negative infinity. Look at this one. Leading term. You see the leading term? This is your leading term. You have to simplify it. X fifth over x squared would be x cubed. And you know the limit of x cubed when x goes to negative infinity would be negative infinity. This last case always going to be infinity, but it may be positive or negative, okay? So if the power of the top is higher, there's going to be leftover on the top. Nothing on the bottom. So this limit is always positive or negative, okay? So shrinking. So the limit of, just rewrite, x to the 5th, 2x plus 1, x squared plus 7, x goes to negative infinity. So it's equal to the limit, remember, limit. If you don't write, you cannot write it without limit. Some people, they do. So leading term, x to the 5th, leading term, x squared. Simplify x fifth over x squared is going to be x cubed. Okay, this would be simplify x cubed on the top, nothing down the bottom. So it's going to be limit of x cubed, but x goes to what? Negative infinity. And we talk about it, negative to the odd power would be negative. So this limit is negative infinity. That's it. 3 cases for the rational function. Any question? So if the degree of the top is higher, you may get a positive infinity or you may get negative infinity. If the degree of the bottom is higher, so you get infinity down the denominator, that would be pizza problem. The result is 0 all the time. But if the degree of the top and the bottom are the same, so the top and the bottom would cancel out. So we get these coefficients that we have. Okay, so 1, 2, 3 in the case of the rational function, and we are done. Any question? So I don't use that method of your book to divide them by x squared. If you may have seen it before or you like it, it takes time. That's easy, especially get used to it or, for future application. Okay, so that's a rational function. Any question? The big one is the next one, next group, radical functions. Okay, so let's see, we have a couple of nice examples here. So how are we going to take care of the radical function? And behavior. That shortcut would be so useful here. And behavior of a radical function. Radical functions. Okay, there are kind of 3 cases that we're going to have. Now, you know that the limit of the radical, we did it before. If you want to find the limit of the radical expression, you are going to take the limit inside. When you take the limit inside, it's going to be one of those cases that we already talked about it. That's it. So let's see what's going to be the possibilities. So we'd like to find each limit. Find each limit. Okay, that's going to be the first one. The first one is a standard 1. So you want to find the limit of the radical expression, something like a limit of x goes to positive infinity, and you have this radical. The top, you have a 4x squared plus 3x minus 1. And the bottom is x squared plus x plus 7. Everything is inside the radical. Make sure you write down correctly. You see, as we did before, if you want to find the limit of the radical, if you stay outside of the radical, you are not going to get anything. So in order to get it, you have to go inside the radical. Okay, so take the limit inside. Solution. So we have to rewrite. I rewrite it, we can. So this is the given one. 4x squared plus 3x minus 1 over x squared plus x plus 7. Take the limit inside. It's going to be the limit of this rational function, 4x squared plus 3x minus 1 divided by x squared plus x plus 7. You see, x goes to positive infinity. Now, what type of function do you have? You have a rational function. How are we going to find the limit at the infinity of rational function? Remember, leading term. Leading term. Here you are. 4x squared and x squared, x squared and x squared would cancel out, and that give you 4. So this is going to be equal to the limit of, it's going to be the limit of the leading term, shrinking for x squared over x squared. X goes to positive infinity. So x squared and x squared would cancel out. You get 4. So it's going to be radical 4. And the radical 4 is equal to 2. So the limit is 2. Nice and easy method. Okay, to be able to get this true. Any question? So if you have a single radical, the limit of the radical expression, of course, is going to be, we take the limit inside. So that's a case 1. Okay, the warm-up, if you like. But the case that you're going to have is going to be, you may get the combination of the rational function and the radical function. So this means this radical may be on the top or on the bottom, just one of them. Okay, so this is going to be your official example that you need to know. Okay, this is it, number 2. And that shortcut again is so useful for this case. Limit of x goes to negative infinity. Okay, this is it. 3x plus 1 on the top is square root of x squared plus 5x on the bottom. Look at this one. That's a typical example that we're going to have. Okay, let's say I'm going to do it. You see, it's a rational function. So you have to find the limit of the top divided by the limit of the bottom. But the top is a polynomial. And in order to get the limit of the polynomial at infinity, we just take the limit of the first one. So we shrink the top into the 3x. That's the top. Bottom. Bottom one is a radical function. If you want to find the limit of the radical function, you have to go inside the radical. If you go inside the radical, x squared plus 5x is a polynomial. And the limit of the polynomial is the same as its shrinking function, which is x squared. So basically, this means shrink the top and the bottom. See, you shrink the top and the bottom, and you take the limit of this quotient, and you're done. Okay, so the solution is going to be, you don't have to rewrite it to explain it. So again, that method of your book is going to be complicated for this one. X goes to negative infinity. Shrink the top, so it's going to be the limit of x goes to negative infinity, so the top would be 3x. And the radical inside the radical, you shrink it into the radical x squared. But the only catch is this one. What is radical x squared? It's going to be happen for all of them. Any suggestion? Radical x squared. Let's see, we have one suggestion here. Yeah, of course, yes, Genova. That's it, absolute value of x. Make sure you use the absolute value. Remember, radical x is not x, it's not positive negative x, it's absolute value of x. And that's a very important for this type of problems. Okay, it's going to be 3x. It's going to be absolute value of x. So you write as an absolute value of x, then you decide. You know that the absolute value of x would be x if x is positive. Absolute value would be negative x if x is negative. You look at this one, you see x goes to negative infinity. Since x goes to negative infinity, this means x is negative. Okay, I just remind you, this is the explanation that say, oh, but x is negative. So when x is negative, my absolute value of x would be negative x. Okay, so this means this is going to be equal to the limit of, the top would be 3x. At the bottom, make sure you replace it by a negative x. And x goes to negative infinity. Okay, that's it. You simplify the x and the x, the result would be negative 3. Okay, you got to be careful if it is going to be if x goes to positive infinity. If x goes to positive infinity, then this absolute value of x would be just x. So your answer would be positive 3. Okay, so this is one of those cases that you have to be careful. Which one is it? So make sure you use the absolute value here. Use the absolute value. It depends whether it is a negative infinity, positive infinity. You may get x or negative x. That's why I should give another example to make sure you know it. Any question? Very easy method, you see. So shrink it all the time. That's a very nice, nice method, if you like, those like the big O notation that we have. So let's have another one to check x goes to positive infinity, but the radical may be on the top. So it may be on the top or maybe on the bottom to finish it. Okay, so this is going to be another option that they may have. Number 3, you want to find the limit of, okay, the limit of x goes to positive infinity. This time they put the radical on the top. It doesn't matter. Radical 9x squared plus 7 on the top. And you have 5x plus 1 here. You see that's 1. Again, now you know it. You shrink the top and the bottom, and the top would be shrinking to the 5x. Inside the radical would be shrinking to the 9x squared. So basically, this is going to be the solution. You keep the limit, remember, limit of x goes to positive infinity. Okay, sorry. X goes to positive infinity. I have to repeat that one, and then I shrink it. So it's a radical 9x squared plus 7. And this is going to be 5x plus 1. So it would be the limit of it shrinking 1. So you shrink the inside the radical into the 9x squared. The bottom one you shrink to the 5x. And make sure you use the absolute value. Okay, on the top. So it's going to be the limit of x goes to positive infinity. So the top would be absolute value of 3x. The bottom one would be just 5x. Let's check to see what type of x do you have, positive or negative. X goes to positive infinity. So x goes to positive infinity means x is positive. So remind yourself, you don't have to write this, I just write it down. X is positive. So the absolute value of 3x becomes 3x only. Okay, 3x only. So the result is going to be what? It's going to be the limit of, keep the limit all the time, 3x and 5x. And x goes to positive infinity. You simplify the x's, the result would be 3/5. The final answer. Okay, very nice method. Just keep it in order, and everything would be fine. Okay, any question? Now there are two more tricky examples. I give you a break now and we come back and we do it and then we finish with the limit at infinity. Okay, just as I told you, we give you one problem of this on the next test. Okay, it's going to be two parts. The first part is going to be kind of a rational function. The second one, the radical function, and the next two examples are a little bit different. So you will see one of them on your next quiz. Okay, so it's almost 9:13. Okay, we come back in 10 minutes, 12 minutes. Let's come back around 9:25. Okay, and then we continue, give you those two examples and we finish this section. As I told you, this section are not going to be used directly, but it would be very, very useful to know it. And then of course we come back to these limits at the end again. So see you then. Okay, let's continue. Any question? We have two special examples that we have to cover. Okay, so these are the usual one that you're going to have, when you're taking care of these problems. But the one which is going to be different is this one. You have 4 of these in your book, in your assignment. Just want to make sure that we are not going to use it through this course. That's not bad. You want to find this limit, you see, the limit of, that's going to be the limit of and that's the square root of x squared plus 3x plus 1 minus x, and this is going to be x goes to positive infinity. So the type of function that sometimes we use in application, and if you want to graph it, or if you want to find this so-called vertical asymptote, then it would be useful to operate. Okay, there you are. You see what's going to be different about this one is that it's not going to be a rational function. Okay, when x goes to positive infinity, as usual, you take the limit. It's going to be limit of the first one and the limit of the second one. Limit of the first one minus the limit of the second one. Limit of the first one is the limit of the radical. We have to go inside the radical. So we take the limit of this expression, which is a polynomial. So the limit of the x squared plus 3x plus 1 is the same as the limit of x squared. And when x goes to infinity, so the result of the first one would be a positive infinity. Minus the limit of the second one, which is a polynomial, leading term is just the x, so that would be negative infinity. So basically, if you want to find the limit, so that give you the limit of the, x squared plus 3x plus 1 minus x, and x goes to positive infinity. So that would be simply a positive infinity for the first part. It's going to be minus infinity for the second one. Okay, so that give you the case. Of course, infinity is not a number, so you cannot cancel out this. So we call it indeterminate form. Means there is a solution. There are many solutions, but we cannot determine that which solution is going to be for this one, to determine the one for this given one. So what you have to do is, we can do it if it's going to be a rational function. So you have to change this one into a rational function. The way we're going to do it is that you need a little bit of algebra. So you're going to start with the given one, then you multiply it and divide it by its conjugate, because you want to remove these radicals. So the conjugate would be this, the first one, a plus x. So it takes a little bit of time to do that job. So this is the way you do it. You start with the given expression. Okay, so that gives x squared plus 3x plus 1 minus x. When x goes to positive infinity, so you have to rewrite it, is the limit of, you change it to the quotient. So you get whatever you have. This is x squared plus 3x plus 1. Okay, minus x already, you multiply by its conjugate. The conjugate is this one, that you just change the middle sign, is x squared plus 3x plus 1. But this is going to be plus x. Okay, divided by the same thing. So that gives you x squared plus 3x plus 1 and the plus x. Okay, so this is your extra term that you multiply the top and the bottom by its conjugate when x goes to positive infinity. Okay, so we want to change it to the kind of a rational function to be able to take care of it. But we stay on the top to simplify it. You know, there's a special FOIL. It's like a minus 3 minus times a plus, as you did it before. It's going to be the square of the first one. So when you multiply, it's going to be the limit of x goes to positive infinity. Okay, it's going to be the square of the first one, which is x squared plus 3x plus 1 all squared minus the square of a second one, which is a minus x squared. The bottom one would stay the same. So that gives you x squared plus 3x plus 1 and plus x. You stay on the top, you remove this radical. So this is going to be the limit of x goes to positive infinity. Now the top would be x squared plus 3x plus 1 minus x squared. And the bottom one is just x squared plus 3x plus 1 and the plus x. So we get a chance to simplify the top. You see the x squared and x squared cancel out. Now you get something like the previous problem. Okay, so this is going to be just, you change it into the format that you'll be able to handle it. It's a 3x plus 1. And on the bottom, we get the x squared plus 3x plus 1 and the plus x. Okay, when x goes to positive infinity. Any question? So you need this extra action. Now you change it to the whatever we did before, you see. You shrink the top into the 3x. But the bottom one, you have two terms to shrink. The radical one, you see this is going to be the shrinking of the top. The bottom one is like the sum of two limits, if you like, two function. So you shrink the first one inside as a radical x squared, and this would be stay as x. So basically this is going to be equal to the limit of, the top would be 3x. The bottom one inside the radical gave you radical x squared, and outside the radical give you x, and x goes to positive infinity. Any question? Some people, they miss this one. They just shrink the first one. It's a two function, okay? The radical function and the polynomial function, or the x function. So for the radical one, make into the radical x squared, and for the x, this is the one. Remember, radical x squared with the absolute value of x. So we continue. Try to, if you can, I can read it over here so we can have it. So this is going to be equal to, okay, it's going to be equal to the limit of, so the top I have the 3x, so this would be absolute value of x plus x goes to positive infinity. But remember the x is positive, so I can drop the absolute value. So remind ourselves that the x is positive, so I can drop the absolute value of x into the x. So I get the limit of 3x on the top, and I have x plus x. X goes to positive infinity, so that gives you 3x over 2x. So that gives a limit of the 3x over 2x. X goes to infinity, you drop the excess. So the final answer is going to be 3/2. Okay, of the total, the problem. The total is, from algebra point of view, it's nice to be able to do it, but we are not going to use it. You have only one of them in calculus 2 that we are going to use. Okay, but getting to know this method is going to be popular case. Okay, any question? But there is one more. This is going to be used quite a lot. Okay, use this one quite a lot in calculus 2, and if we intend to take calculus 3, is going to be the case that we're going to use it quite a lot, and we give one of them on the test. Okay, we are not going to be interested in these for the test. Okay, but it's nice to know the techniques. Okay, but the next one is the one that you will see it. Okay, are you ready? So the most important one for future, I just break it into new format so you know that they are important. So there are kind of two different types of limits. There are a couple of more, that we cannot do it now, but we do it at the end of the course. So these two limits are going to be used quite a lot. Find each limit. You did a similar one before. For the ordinary limits, now this is the limit at infinity. So there are going to be two. The first one is this one, something like the limit of, you see on the top, it's going to be sine x. And then the bottom is going to be a power of x. Doesn't matter. X squared, x cubed to the fifth radical x, cube root of x. I'll go with the x squared here. And it's going to be x goes to positive infinity. In calculus, so we use sequences rather than this type of function. Sequence is a function whose domain is positive integers. So they use n instead of the x. So it's going to be a limit of sine n over n squared, n goes to infinity, the way you are going to use it in future. Now, as we did it before, so you see, you cannot shrink it. There is a shrinking one for this one that we are not going to discuss. But as you did it before, there are the two different methods, three different methods to do it. But at this level, we are going to use the squeeze theorem. Remember the squeeze theorem, you squeeze it. The squeeze theorem is true for any limits. It's a limit at infinity, so it's not a big deal, so we can use it. So to do it, a squeeze theorem solution. So it's good practice to remind you the squeeze theorem again. Remember, you have to squeeze this one between two numbers like you did it on test 1. So we start with the sign because we know that the sign is, so this is it. Note that the sign is sine x is always between 1 and -1. But remember, in this case, in the previous problems, it was the power of x times, it's the power of x divide. So what you're going to do, you are going to divide by x squared, whatever power you need. So divide by x squared, 1 over x squared, less than equal to the sine x over x squared. And this is going to be 1 over x squared. Here you are. You don't have to worry about x not equal to the 0 because x goes to positive infinity. Now that's it. You squeeze the function within two other functions. So take the limits of the function to the right, to the left, but you take the limit at infinity. And both of them are just a pizza problem. Okay. So over here, the limit of the -1 over x squared when x goes to positive infinity would be 0 because the hole on the top or the degree of the bottom is higher. And over here, the same thing. The limit of 1 over x squared, x goes to infinity would be 0 again. Here you are. So by a squeeze theorem, okay, so this is it. It's going to be by a squeeze theorem, the limit of the middle one is going to be 0 as well. So the limit of the sine x over x squared, x goes to infinity or positive infinity would be 0. You see, this is the way we do it. Okay, quickly we can take care of it. So you must know that this is different, the application of the squeeze theorem, and you just nicely squeeze it between these two. Okay, any question? So this is one that we're going to use in future. I'll give you another one with the cosine to finish it. Okay, that was case 1. Case 2, just remind you that you may have this one. So how about the limit of cosine x, and this is going to be cube root of x. Okay, when x goes to positive infinity again. It's very similar. Just wanted to see that, sine or cosine, you may have it. And over here, you may have a radical function, doesn't matter. Okay, radical x, okay, cube root of x would be fine. So again, you have to squeeze it. We start with the cosine x, the only thing that we know. This type of problems comes with the sine and the cosine. Okay, so we get the solution here. And we go with the sine. So note that we have the sine x between 1 and -1 again. Oh, I'm sorry, I made a mistake. I need the cosine. Okay, so this is going to be cosine. I rewrite it. So the cosine is between 1 and -1. But you want it to be divided by cube root of x. Divide by cube root of x, it doesn't matter. Because x is not going to be 0, it's goes to positive infinity. So we are going to have a -1 over cube root of x. Okay, less than equal to the cosine x over cube root of x. And this is going to be less than equal to the 1 over cube root of x. There you are. So we squeeze it, and then you know that these are all just pizza problem. If like x goes to infinity, bottom is infinity, that would be 0, but we have to write it down. So the limit of the -1 over cube root of x goes to infinity again is 0. This one over here, the limit of 1 over cube root of x goes to infinity is 0. So again, by a squeeze theorem, limit of the cosine x over cube root of x goes to infinity is going to be equal to the 0, and then you're done. Okay, so this is a kind of true special one really that you are going to use quite a lot in future to get this true. Okay, so that is the end behavior, or that the section that I talk about, 3.5. 3.6 is a graphing the these functions. We can use graphing calculator to graph it, but there are a couple of them. These at this level, they are all polynomial types and nothing to worry about. But if you want to graph a function in calculus, you have to do quite a lot if you're going to be serious, because you need to collect the information. You have to work on the f prime and use first derivative test to find out where the function is going to be increasing, decreasing. Use the second derivative to get the concavity. You find the x-intercept, y-intercept, put them together. But we are going to do just a couple of function containing the natural log and the ln function at the end of the course. So that's why you can read 3.6 yourself and graph those functions using your calculator. We are not going to cover that section, so that will take us to the 3.7. I let you go today because to prepare for your test. So the next section that we have, 3.7, is optimization problem, that we can discuss that one tomorrow to give you a little bit of time to prepare for the test, and then we come back and we finish these two sections tomorrow. 3.7 optimization. Optimization problem is a situation that you have something that you want to maximize or minimize it. Again, depends on the discipline they are going to use in future. But what we do, we just give you a couple of general examples to take care of it. So it's a 3 examples